Great. Good afternoon and good morning to everyone. Thank you for attending the CXL Consortium Vertical Optimization of the CXL Stack webinar. Today's webinar is presented by the Samsung Memory Division, and I will be handing it off to the team to begin the webinar.
Hello, everyone. Thank you for joining this webinar. It's my pleasure to be here. I'm Jin So, Senior Director and System Architect, Head of the Memory Architecture Group at Samsung. I currently lead our CXL product development and technical research. It is a great honor to represent Samsung at the CXL Consortium and introduce the three of our key CXL technologies designed specifically for the AI application. Okay, first page. As we move toward agentic and physical AI, the demand for memory is exploding. This is largely driven by multimodal inputs. According to our recent experiments at Samsung, processing video requires 8 times more KB cache than processing simple text, as like the left chart. To give you a concrete example, look at robotics. If you want a robot to function for just 15 minutes with 10 actions per second, you need about 1.2 terabyte of memory just for the KB cache. Furthermore, this data needs to be maintained as a form of long-term memory for the future reuse. In today's industry, CXL memory has emerged as the most realistic solution to meet this massive memory demand. We are already collaborating with many customers to build actual use cases. One of the most frequent requests we receive is to manage KB cache with higher performance and low TCO than existing RDMA-based sharing systems. Customers also want to use the pooling technology to isolate services for the different AI agents and maximize memory efficiency. To meet these needs, we have optimized the CXL memory system across three dimensions: latency, bandwidth, and capacity. This optimization spans both hardware and software. Today, I want to walk you through the three technologies that make this possible. The first technology focuses on latency. We all know that CXL naturally has a little bit higher latency compared to the traditional DIMMs, the local memory to the CPU. To bridge this gap, Samsung developed SCHMU, the CXL hub page monitoring unit. SCHMU is designed to compensate for that inherent CXL latency at the system level by device page migration support. By implementing this, we managed to improve the latency perceived at the application level by 40%. This effectively allows applications to experience performance that is nearly similar with the standard themes, removing the primary barrier to CXL adoption. The second challenge is bandwidth. In many cases, the PCI bandwidth used by the CXL is lower than the native DRAM bandwidth. We address this bottleneck with the CXL PNM, the process near memory technology. CXL PNM utilized the data reduction techniques to overcome the physical limits of the interface. Instead of moving low data back and forth, we process and reduce it near the memory. This approach has allowed us to deliver a 5 times more bandwidth increase in effective bandwidth for the application. It ensures that the data flow stays fast enough to keep up with high performance AI workload. Finally, we have the issue of stranded memory, which is a significant pain point in modern data centers. To solve this, we are introducing Tangier version 2, a Kubernetes-based memory orchestration solution. Tangier version 2 manages memory resources dynamically. It minimizes wasted, idle memory across the cluster and reallocates it where it's needed most. By using this orchestration layer, we have improved the effective memory capacity by approximately 50%. This allows the data centers to do much more work with the hardware they already have. Okay, that was my introduction for today's webinar. So from now on, we will explain the details for each technology.
Hello, this is Wonjin Lee from Samsung Electronics, and I am responsible for the host side software of the CXL tiered memory system. Today, I will talk about hot page monitoring, which is a critical issue in CXL-based system. I will first explain the limitation of host-based approaches and then introduce a device-based approach to address them, namely CHMU, which has been incorporated with the CXL specification. I will also present the practical implementation and evaluation results. So, why hot page monitoring matters? As you all know, CXL memory inherently has higher latency than DRAM. This is mainly due to the PCIe bandwidth interconnect and protocol overhead. In practice, when a CXL switch is introduced, the latency to CXL memory devices becomes even higher. As a result, if memory is used without careful consideration, it naturally leads to performance degradation at both the applications and system levels. The fundamental idea of mitigate this is straightforward. Frequently accessed data should reside in DRAM, while less frequently used data should be placed in CXL memory. In other words, hot pages should be placed in higher tier memory and cold pages in lower tier memory. This naturally improves application performance. However, this introduces key questions. How do we accurately determine which pages are hot? Traditionally, host-based techniques such as AutoNuma and daemon in the Linux memory management subsystem has been used for this purpose. However, these approaches require continuous CPU involvement, which introduces software overhead and limits performance. Then what if this task is offloaded to the device? In the case, we can reduce host resource usage and potentially improve accuracy. So let's take a closer look at the limitation of existing host-based approaches. There are two main issues, CPU overhead and accuracy. For example, NUMA balancing works by modifying the state of selected PTEs to intentionally trigger page faults. This mechanism, commonly known as NUMA hint faults, introduces significant overhead on the CPU side. Since these faults are used to make page migration decisions, they inevitably consume a considerable amount of CPU cycles. MPTE scanning approaches have similar limitations. They require scanning all PTEs in their target lesion, which is costly, and they rely only on the single access bit, which limits the granularity of the information. In other words, the access bit only indicates whether a page was recently accessed, but it does not capture access frequency or temporal patterns. So as a result, the accuracy is inherently limited. Daemon, for example, reduces overhead by using a sampling-based approach instead of full PTE scanning, but this comes at the cost of reduced accuracy. And similarly, sampling-based techniques such as PBS cannot fully capture all memory accesses, and increasing the sampling rate can improve accuracy, but it also increases the number of profiling events, leading to higher CPU overhead. In summary, host-based approaches have a structural limitation. They incur high cost, yet provide limited information. To address these limitations, device-based monitoring has been introduced. The key idea is simple. Identify hub pages directly at the device where memory accesses actually occur. This approach reduces CPU involvement and enables more accurate observation of access patterns since the device can monitor memory transactions at a finer granularity. And this is the motivation behind CHMU, the CXL Hot Page Monitoring Unit. With CHMU, the host continues to manage page temperature using traditional policies such as LRU, while the device provides additional harness information for CXM memory. This enables the intended behavior of tiered memory systems, demoting cold pages from DRAM and promoting hot pages from CXM memory. An important point is that this is not just a research idea. Industry requirements were first discussed within the OCP community and then standardized through the CXL Consortium. Therefore, CHMU is expected to play a key role in future tiered memory systems. As defined in specification, CHMU collects hot page information at the device level and provides interfaces for the host to read this data, along with event and threshold-based notification mechanisms. The effectiveness of CHMU was validated in our previous work, and the results were published in IEEE Transactions on Computers under the title Steering. I will explain this in more detail in next slide. Implementing per-page access counting in hardware is not trivial. A straightforward approach is to maintain a dedicated counter for each page. However, this quickly becomes impractical as memory capacity increases. For example, with 128 gigabytes of memory, more than 30 million pages need to be tracked. Storing counters for all of them would require tens of megabytes of memory, which is significant overhead for the device. To address this, we changed our approach. Instead of tracking everything exactly, we adopted the probabilistic estimation method. After evaluating several probabilistic data structures, we found that count mean sketch provides the best trade-off between accuracy and hardware cost. Counter mean sketch is well-known probabilistic data structure for estimating frequency in streaming data. While I will skip the detailed mechanics, it uses a limited size of counter table and still achieve high precision with relatively low error, as shown in this figure. Although CMS introduces some estimation error, it is sufficiently accurate for identifying hot pages. And returning to our system, let me go to the previous page. We implemented this hardware on FPGA and extended the vanilla CXL device driver to support CHMU standard and deployed the corner daemon that migrates hot pages to local DRAM. Our observation shows that even a simple policy can significantly improve performance across multiple applications. And finally, Let's briefly look at the impact of CHMU. In conclusion, the performance improvement is substantial. You observe up to approximately 3 times speed up compared to the baseline first touch policy, and it also outperformed AutoNuma. The reason is that hub pages are gradually migrated to DRAM, reducing access to slower CXL memory. As a result, DRAM bandwidth utilization increases and overall application execution time decreases. This is not only due to latency reduction, but also because reduced CXL traffic alleviates bottlenecks. In real workload, we observed that hub pages progressively moves to DRAM over time and performance improves accordingly. In summary, CHMU is not just a conceptual idea, but a practical solution that delivers meaningful performance gains in real systems and applications. So, to conclude, device-based hot page monitoring is essential to overcome the limitation of host-based approaches, and CHMU provides a practical and standardized solution uh, for this problem. Thank you.
Hello, everyone. My name is Hojin Nam, and I'm from Samsung Electronics, and I'm participating in developing CXL and PNM host software. So today, I will talk about CXL PNM, process near memory. And this is a technology we are developing to overcome bandwidth constraints in AI workload. So I will start by explaining the bandwidth bottleneck problem in CXL systems, then show how CXL PNM addresses it, and finally present a proof of concept demonstration with real results. So CXL memory pooling is a powerful technology. It allows us to connect many memory devices through a switch. And as we add more devices, the aggregate memory bandwidth also increases. So this is one of the key strengths of CXL systems. Let me explain with the example on this slide. So we have two upstream ports and each providing 64 gigabyte per second bandwidth. And we have six CXL devices and each providing 32 gigabyte per second bandwidth. So each upstream port is connected to three devices. So the aggregate bandwidth from three devices is 3 times 32. That is 96 gigabyte per second bandwidth. But the upstream port can only deliver 64 gigabyte per second. This means 32 gigabyte per second of bandwidth is lost. It simply cannot pass through. And as we add more devices, this gap becomes even larger. For memory intensive AI workloads, this bottleneck is a critical problem. So instead of trying to increase the upstream bandwidth, we focus on improving how the bandwidth is used. The way we do this is by reducing the amount of data that needs to travel over the CXL link in the first place. So the key idea of CXL PNM is to reduce the amount of data transfer over the CXL link. Let me explain why this is important using vector search as an example. So in vector search, we compare a query vector against a large number of stored vectors. This means that for each query, we need to access a large amount of data from memory. In a conventional CPU-based system, all of these vectors must be transferred from memory to the CPU. So for each query, vectors are fetched from memory and transferred to the CPU and then processed. In this process, the amount of computation per data element is relatively small, but the amount of data movement is very, very large. So system becomes memory bound rather than compute bound. In a CXL system, this data movement also goes through the CXL link. With CXL PNM, we change where computation happens. Instead of moving large amounts of data from CXL device to the CPU, we move the computation closer to where the data resides inside the CXL device. So the data flows change like this. Before, large data moves from memory to the CPU for computation. After, the device processes the data locally by transfer command, and only the reduced result is returned. So the amount of data transfer per operation is significantly reduced. So now let me show how this reduction in data movement improves the overall system. In this diagram, some of CXL memory devices have been replaced with CXL PNM devices. Each CXL PNM devices integrate large capacity memory, high internal bandwidth, and integrated processing cores. Because each PNM device processes data locally, only reduced users need to pass through the upstream port. This means the system can process more operation within the same bandwidth constraint. We are not increasing bandwidth, we are using it more effectively. And this approach enables scalable performance even with a fixed CXL bandwidth. So let me now introduce a concrete use case, vector search in RAG system. RAG is widely used in modern AI applications. It retrieves relevant information from a large database before generating an answer. So vector search is the core operation in RAG. It compares a query against a large number of stored vectors to find the closest matches. This is a highly memory-intensive workload. We implemented this using the FICE, a widely used open source library for vector search. In FICE, search goes through two stages. The first, core search, it is identifies candidate clusters and it is relatively lightweight. Second, fine search, compares the query against many vectors and it is very memory intensive workload. So in our approach, the core search stays on the CPU as usual. The fine search, the most memory intensive part, is uploaded to the CXL PNM device. So on this slide, you can see the code comparison. So the left side is the original FICE code, and the right side shows our modified version. So we added just a few lines to redirect the fine search to the PNM device using our API. In summary, first, the vector index is generated from the dataset. Then the index is loaded into the CXL PNM device. And after that, at query time, the CPU handles core search and the CXL PNM handles fine search. Let me now walk through our proof of concept demonstration. So the server uses CXL 2.0 capable CPU with 40 cores. And we connected first CXL PNM device to the host, and each with 32 gigabyte of memory and interface through a PCIe Gen 5 by 8. For the workload, we used files with index IVA flat, and we assume that all vector-DB data resides in CXL memory. So we compare two cases, CPU-only execution versus CXL PNM. CPU only achieved 3.5 cores per second. And with CXL PNM, we achieved 19.7 cores per second. And that is more than 5 times the core throughput. As you can see on the monitoring graph, when using CXL PNM, the PNM engines take over the computation, and we can confirm that the whole CPU utilization is significantly reduced. So this frees the CPU for other tasks. By reducing data movement and leveraging near memory computation, we achieve significant performance improvement in a real AI workload. So let me summarize what we have covered today. So CXL enables scalable memory system with high aggregate memory bandwidth. However, CXL switch system have a fundamental bottleneck at the upstream port. So by combining CXL with PNM, we reduce data movement and improve how bandwidth is used. This allows the system to perform more work under the same bandwidth constraint. The work I presented today is at the research stage, and we are looking forward. We are exploring extending this approach to KV cache offload to CXL memory and supporting additional vector search format beyond IVA flat in rack system. So this is one possible direction for improving efficiency in future CXL-based system. Thank you very much for your attention.
Hello, good afternoon and good morning, everyone. Thanks for joining this webinar. My name is Han Deok-ri, Principal Engineer in the Memory Architecture Group at Samsung. In this part, I will introduce the CXL 2.0 based memory pooling solution, namely Pangea V2, a dynamic rack scale disaggregated memory system integrated into the cloud-native Kubernetes environment. Specifically, I will show you how the open source of the Pangea V2 software stack systemically eradicate critical technical void within the ecosystem. Furthermore, I will present the economic imperatives for enterprise data center and the common company-wide uses and the tangible application effect. Although the advent of the CXL 2.0 and the latest 3.2 specification successfully established the foundational hardware blueprint for multiple forced memory pooling and sharing via dynamic capacity devices. The software ecosystem required to dynamically allocate the control these advanced hardware resource for real-world data center workload remain in an incomplete trajectory. During the CXL 4.0 technical training event, Anil, the chair of the CXL Consortium Marketing Working Group, articulated the indispensable key element necessary for successful construction of the memory pooling ecosystem in his presentation titled The Challenge for Memory Pooling Ecosystem. According to his comprehensive address, formulating a flawless CXL ecosystem demand a seamless synergy of the CXL supported host CPU from the Intel and AMD, high performance CXL fabric switch chip from entitled like Marvell or Panacea, the global fabric attached memory devices manufactured by Samsung and Micron, fabric control software, memory middleware, and crucially, the high-tier orchestration software governing these vast resources. While hardware device and firmware level technologies are advancing at a breakneck pace, the objects of this top-tier orchestration layer, which serve as the vital conduit between end user application and the underlying hardware, act as a significantly bottleneck, impeding the commercialization of the CXL technology. Pangea represents a comprehensive integrated hardware-software architecture that combines the ASIC-based CXL switch with the CXL memory to dynamically provision pooled memory within existing Kubernetes ecosystem, entirely circumventing the need for application code alterations or operating system disruption.
Pangea is the POC project name, and each version of the Pangea system follows the corresponding version of the CXL specification. The most innovative feature of the CXL 2.0 based Pangea V2 architecture is it supports the seamless runtime dynamic capacity adjustment. Traditional virtualization and the container platform require a memory to statically allocated at the time of the instance creation, a practice that directly contributed to 23% of average utilized rate observed in the major cloud cluster. NGF allow the physical binding and the unbinding of the CXL memory devices to work node in real time, thereby bridging the gap between resource demand and provisioning. The fundamental software architecture underpinning in this system is the distinctly bifurcated into lower layer, the CXL agent, tasked with the physical infrastructure management, and the upper layer, the data center memory fabric management, responsible for logical memory provisioning within Kubernetes cluster. The CXL fabric infrastructure within data center will inherently feature highly complex topology composed of switches and devices from various vendors. The Pangea V2 CXL agent is robustly engineered on the open fabric management framework recognized as the Sunfish framework established by Open Fabric Alliance to effectively abstract this heterogeneous complexity. The function of this agent involved translating the unique command line interface or proprietary fabric manager API inherent to individual bandwidth vendor switches into standard the DMTF Redfish RESTful API format in real time. Subsequently, the serving these to the overarching memory orchestrator. From a perspective of the technologically advancement, the legacy Redfish specifications were limited in their capacity to fully represent indispensable CXL 2.0 feature. The CXL agent in Pangea V2 ingeniously introduced the virtual CXL switches and the virtual PCI to PCI bridge object into the Redfish data model tree, successfully proposing and integrating them as the global standard specification. Positioned directly above the CXL agent is the DCMFM manager, a memory composability layer that stringently implemented the OCP composable memory system architectural specification. DCMFM Manager facilitated the stable execution of the memory-intensive application path on the worker node within Kubernetes cluster, negating the requirement to procure expensive, specialized bare metal node equipped with a massive memory. DCMFM achieved the granular resource managed by dividing CXL device into mem blocks, unit of the 128 megabyte or 2 gigabyte that aligned with the Linux kernel hard plugin management. This enables a single physical device to be shared across the multiple nodes. Furthermore, this MFM manager supports the interleaved allocation policy across the multiple devices, which maximize all the memory bandwidth. The value of Pangea V2 software stack lies in its ability to empower end user to provision CXL memory seamlessly using existing Kubernetes specification. means a pod spec, completely eliminating the need to modify complex application code or custom script. Performing this crucial link role to ensure such a transparently usability is the CXL node resource interface plugin, which interfaces directly with the container runtime interface, such as containerd or CLI. The CXL NRI plugin intervene the container lifecycle to adjust the resource in real time without modifying the underlying operating system or Kubernetes binary. The workflow for dynamic memory allocation proceeds as follows. Uh, a data center operator requests the creation of the new pod via Kubernetes API. Using standard command like kubectl apply with pod YAML file. Concurrently, the resource annotation field with the pod YAML file specification is explicitly declare the attribute memory type, CXL alongside the required memory capacity for execution. Upon the workload CRI runtime detecting the sandbox environment creation event for new pod, the run pod sandbox hook internal to the CXL NRI plugin is instantly triggered. Interbeing via this hook, the NRI plugin formally requests the location of the specified memory capacity from the CXL pool by invoking RESTful API directly at the worker node DCMFM agent. The DCMFM manager receiving the request for optimal command SMMD device according to the pre-configured policy. Subsequently, it commanded the CXL agent to physical bind the logical region of the selected device to the worker node VCS. Following the successful bind, the DCMFM agent changing the 2 GB offline memory block into online state, which is registered in the Linux system RAM topology, transitioning them into actual available memory. Upon completion of workflow processing and pod termination, the stop pod sandbox hook is generated. The DCMFM monitored aggregated this termination event globally across the cluster, revert the mem blocks occupied by container back to the offline state, and execute the switch port unbinding process via the CXL agent. Safely return the resource to the main memory pool. Due to the fundamental disparities in the data transmission mechanisms, the CXL 2.0 based Panjabit architecture deliver revolutionary performance enhancement and the TCO reduction effect compared to legacy infrastructure reliant on RDMA. To emulate the application environment, frequently operating with the actual enterprise data center, we used the YCS workload was executed, targeting memcached and Redis in-memory database. The result proved the CXL-based memory pooling's superiority across all metrics. From the perspective of the enterprise data center and the OEM customer, the existing tangible financial tissue reduction impact in line in the capability to maximize Kubernetes pod density within the single server. For instance, when deploying heavy inference or database part consuming 10 gigabyte of memory on the physical load equipped with the strictly limited local DRAM memory of 30 gigabyte. Traditional system hit the physical wall, completely seeding system expansion at the exactly three-part deployment. However, by applying the Pangea V2 software stack, even if the node's local memory is exhausted, the necessary memory is supplied in real time on demand from the CXL memory pool. Consequently, six or more pods can be operated stably with a single server without any interruptions. Although examining the an individual isolated part may be reveal minor performance degrees, approximately 10, 14% due to the CXL remote access communication, densely packing and concurrently operating a great number of the pod with a single physical server prove the phenomenal scale-out effect, elevating the total system throughput by up to 5 times compared to the running a single pod. Okay, finally, as a part of our hope contribute to accelerating the arrival of the next generation memory-centric computing era through the open innovation ecosystem driven by CXL 2.0 based Pangea V2, we look forward to seeing you again, CXL 3.0 based solution. Thank you.
Thank you, everyone, for joining the CXL Consortium webinar, and thank you to the Samsung Memory Division team for sharing their expertise. If you did have any questions, you can share that in the Q&A chat bot, and we will address those questions in our future blog. So please follow the CXL Consortium on LinkedIn for updates. The presentation recording will be available on the CXL Consortium YouTube channels, and the slides will also be available on the CXL website. Once again, thank you for attending this vertical optimization of the CXL stack webinar, and I hope you have a great afternoon.